In this video, we're going to continue our discussion on how to graph polynomial functions. In this video, we're specifically going to look at zeros and what they tell us about the graph, as well as what their multiplicity tells us about the graph. So first, let's talk about what are the zeros of a polynomial function. So the zeros of a polynomial function are just the x values that give a function value or a y value of 0. So when we talk about the zeros, those are x values. Specifically, they're x values that make the y value 0. And a polynomial function can have zeros that are real or non-real. It can have some real and some non-real zeros. But since we only graph real numbers, the real zeros are what's going to tell us something about the graph. And specifically, they tell us the location of the x-intercepts. Because the x-intercepts are the points where y is 0. So whatever the x value is at that x-intercept, that is going to be a 0 of the function. We're going to talk a lot more about finding the zeros of polynomial functions in the next couple of sections in our book, but just to give you a little preview here, we're going to do a couple now where we can just simply factor using techniques we've used before. And then in the next couple sections, we'll talk about what to do if our usual factoring techniques don't work, but we still want to find the zeros. So here all we need to do is factor. We can factor by grouping here. There's 4 terms. And if we look at the first pair of terms, they both have degree of at least 2. So we can factor out an x squared there. I'm going to factor out a negative x squared because we know that what's left in the parentheses is going to need to be the same thing that's left in the parentheses from when we factor the second pair of terms. So I'm going to factor out a negative x squared. That's going to change both the signs. They're going to be positive. So we're going to have x plus 2 left. You can always check if you distribute this back in, do you get what you started with? And then the second pair of terms have a 25 in common, and if we factor out a positive 25, we're left there with x plus 2. And so since both of the terms separated by this addition have an x plus 2 factor, we can factor that out as our common factor, and we're left with negative x squared from the first term and plus 25 from the second term. I'm going to switch the order of these here. I'm going to put the x plus 2 here because I'm going to do something with this. I'm going to factor in negative 1 from both of those terms. So the first term is going to be positive and the second term is going to be negative. And the reason I did that is because now this looks more familiar. This looks like something we factored before. That's a difference of squares. And so that's going to factor as x plus 5 times x minus 5. And so remember, we're finding the zeros. So we're finding the x values that would make the y value 0. And so here we can see that if we set each of our linear factors equal to 0, then that gives us 3 different numbers. We get negative 5, we get positive 5, and we get negative 2. Here's another example we can do by factoring. All of these terms have at least one factor of x, so we can start by factoring x from the three terms. And then what's left is a quadratic, so we can factor that with our usual quadratic factoring techniques. We need two numbers that multiply to negative 14 and add to negative 5. So that's going to be negative 7 and positive 2. And so we have x times x minus 7. And we have 2 times x minus 7. Sometimes I see students get so busy factoring the quadratic they forget that we had an x here, right? So just make sure that at the end your polynomial has the same degree as what you started with. We had an x cubed here, so we should see three different factors here that have an x. And so now if we want to know what x values make this equal to 0, we can just set each of those three factors equal to 0. And so we have 0, 7, and negative 2. Those are the zeros of this function. So for both of these examples, these numbers that we found will tell us where the x-intercepts are. But we want to know a little bit more about what's happening at the x-intercept. We want to know, is the graph going to cross the x-axis at the intercept? Or is it just going to approach it and touch it and then turn around and go back the opposite way? And so to know which of those is going to be the case, we can look at the multiplicity of the 0. So the multiplicity of a 0 is just the number of times that this factor appears when we factored the polynomial completely. So every 0, I'm using C here to represent the 0. So those are the numbers, like what we just found, that make the function value 0. If this number C is a 0, you're going to see this factor x minus C in the factorization. For example, 7 was a 0 here, and we saw x minus 7 there. Negative 2 was a 0 here, and we saw this factor, which could also be written as x minus negative 2. And then 0 was a 0, and this factor x you could think of as x minus 0. So if a number is a 0, then you're going to see a factor x minus that number when you factor it completely. And so for each of these, the multiplicity was 1. We only had the x plus 2 factor show up one time. We only had the x minus 7 factor show up one time. And we only had the x factor show up one time. But sometimes you do get the same factor showing up twice in your factorization. So then the multiplicity would be 2 if that's the case. So what we can do is look at whether that multiplicity then is odd or even, and that tells us what happens at that x-intercept. So if the multiplicity of the 0 is odd, then the graph crosses the x-axis at that x-intercept. If it's even, it's going to do something different, and I think the easiest way to remember is to think of a couple really simple examples of functions that we've dealt with before. So here we have f of x equals x cubed. That's the same as x times x times x, right? We don't usually have a reason to write it that way, but that is what it's equal to. And so the only 0 here is 0, right? The only x value we can plug in that would make this function equal to 0 is plugging in 0 for x. And it's because we have this factor which shows up 3 times. So the multiplicity here, so the 0 is 0, and its multiplicity is 3, which is odd. And we know that this graph looks something like this, and it crosses the x-axis at that x-intercept. Now, if the multiplicity of the 0 is even, then the graph is going to touch the x-axis at the intercept without crossing it. And so here's a nice basic example to help you remember that. X squared is x times x. The only x value you could plug in that would make that equal to 0 is 0 itself, right? So that's the only 0. But it comes from this factor x that shows up twice. So the multiplicity of that 0 is 2, which is even. And we know that the graph of y equals x squared looks something like this. So it comes down and touches at the intercept, but then it turns around and goes back. It doesn't actually cross the axis. I don't know about you, I am not good at memorizing things. That's why when it comes to remembering what happens when it's even versus odd, I think these two examples are really helpful. We know that x cubed has an odd multiplicity for the 0. It's got that odd exponent and it crosses the x-axis. Y equals x squared, the 0 has even multiplicity and it touches the x-axis without crossing it. So here's an example of a function. It's already been factored, and this function has a lot of factors actually, even though it doesn't look like it. We have x minus 1 to the 4th here, which means we essentially have this. We have the x minus 1 factor showing up 4 times. And then we have x plus 2 cubed, which means we have 3 factors of x plus 2. So the zeros here, I'm going to make a table. This function only has 2 zeros. There's only 2 numbers you can plug in for x that would make this 0. One of them is 1, right? If you plug in 1 for x, you'll get a factor of 0. And then the other one is negative 2. If you plug in negative 2 for x, you get a factor of 0. Now let's look at the multiplicity of each of those zeros. The 1 comes from the fact that we had x minus 1 as a factor, and it showed up 4 times. You don't have to write it out this way to figure this out. I just wanted to show you an example that this exponent 4 means it shows up 4 times. So when it's in factored form like this, you can look at that exponent, and that is the multiplicity. So the multiplicity of that 0 is 4. And so since it has an even multiplicity, then on the graph it's going to touch the x-axis without crossing. Remember, even multiplicity, think y equals x squared. It touches the x-axis but doesn't cross it. Then the other 0 was negative 2. That came from the x plus 2 factor, which showed up 3 times. We can tell by this exponent here. So its multiplicity is 3, which is odd. And so at that x-intercept, it's going to cross the x-axis. And so now between what we've discussed here and what we discussed in the previous video, we have enough information to kind of do a rough sketch of our polynomial functions. What we discussed here was the intercepts. So we know that those real zeros there are going to give us x-intercepts. We have 1 and we have negative 2. We know that it's going to touch the x-axis without crossing at this one, and we know it's going to cross over here. And in the previous video we talked about the degree of the polynomial and what that tells us about the end behavior. Now this one has been factored, but you can still tell what the degree is. When you write it out like this, I think that kind of helps. If you were to multiply this all out, which would take forever, so we're not going to do it, but if you multiply these first two factors, you get x squared plus some terms that had lower exponents, right? You'd have an x to the first term and a constant term, but x squared would be your highest term. Then you'd take that x squared plus some stuff and multiply it by the next factor. Then you'd have x cubed plus some lower terms. And then take that, multiply it by the next one, you'd have x to the fourth, x to the fifth, x to the sixth, x to the seventh. So this polynomial has degree 7. Now you don't have to write it out to tell that, because if you come up here and you look, you say, okay, I've got 4 linear factors here, and then I've got 3 more. 4 plus 3 is 7. So we know it has an odd degree, which means the end behavior is going to be opposite. So the arrows are going to point down at one end, up at the other end. And to know which end it points up and which end points down, we need to look at the leading coefficient. None of these factors have a coefficient in front of x, right? Well, they do, but it's 1. And then there's not a value out front here of the factors. So if we had like a 2 out front of this, for example, then the leading coefficient would be 2. But it's just a 1 there, and each of these factors also has leading coefficient 1. So when you multiply all this out, your highest power term is just going to be x to the 7th. The leading coefficient is going to be 1. Which is positive. So since we have an odd degree and a positive leading coefficient, we know that we're going to have the left end pointing down and the right end pointing up. And so now we can sketch a graph of this. We know the left end is going to be pointing up. It's going to come up to this x-intercept here, and it's going to cross the x-axis. And then at this x-intercept, it's going to touch, but then it's going to go back up because we know our right end is supposed to be pointing up. So at some point it's going to come down like this, touch, and then go back up, and then it's increasing to the right.